Guys, picture this. You're trying to decide where to go for dinner with 5 friends over phone. Everyone's shouting different suggestions and someone's connection drops out. Two people starts arguing about the same restaurant. Complete chaos, right? Now imagine those friends are servers in a distributed system, and instead of picking a restaurant, they need to agree upon which data is correct. What if they mess up? Maybe your bank account shows wrong balance, your order gets processed twice, or Netflix forgets what episode you're on. Welcome to the world of distributed consensus, one of the hardest problems in computer science, and today we're going to deep dive into Raft, the algorithm that solved this problem so elegantly. They literally named it Raft because it's supposed to be easier to understand than floating in the ocean of complexity. By the end of this video, you'll understand how the systems like Kubernetes, etcd, or MongoDB achieve consensus. You'll know why Raft is a big deal. And honestly, you might even think distributed systems, dare I say it, understandable. So let's dive in. Let's discuss about the 3 horsemen of distributed apocalypse. The first one is network partition. In a network partition, suppose server S1 writes to node 1. Similarly, it also supposed to write to node 2. There is another server that is S2. Consider a scenario that there is a network partition. Server S1 thinks that N2 is dead. Similarly, S2 thinks that N1 is dead. So they cannot see what data is being written. Now, because of this, we have a brain split. S1 assumes that there is only N1 and it needs to keep on appending data to that. Similarly, S2 assumes that there is only N2 and it can only append data to N2. That way we have a different set of data on different nodes, and then it is very difficult to find out which data to append and how to coordinate among the two nodes. Another example can be server failures. Let me take another example: S1, S2, N1 and N2. There's a request that comes to S1 from a client. First, S1 writes to N1, then it tries to write to N2. What if N2 fails? In this case, it is not able to write to N2 as well, and it keeps on waiting for N2 to come up, making the request take so long that it times out. In a way, it is not able to write to either of the server because it is keep on waiting for N2. Then the third scenario can be message delays. Let's assume server 1, we put the value of A to be 10 on server A. Okay. Server B still has the data of A is equal to 5. There's a delay in the writing process, maybe there's a 5-second. In the meanwhile, on server C, S2 does a get request, get A. Since the data is still stale at server B, it tries to read the old data and it sends A as 5. Now this is another problem because there is a delay in writing data. These are some of the 3 problems which Raft tries to solve. Raft is better than Paxos algorithm because Paxos is very complicated and difficult to implement. Because of that, the cost of implementation of Paxos is much higher. In Raft, unlike Paxos, instead of a complex algorithm, we will break down this problem or algorithm into 3 steps. These steps can be parallel steps. One is the leader election, second is log replication, and third is the safety. How do we stay consistent? In leader election, we find who's the in charge. Whereas in log replication, we replicate the data to different servers. We make sure that the data is replicated to all the applicable servers in the required time. For safety, we ensure that how do we stay consistent, how the data is consistent. These are the primary components we are going to discuss about Raft. Let me tell you some of the basics about the Raft algorithm. In Raft, we follow consensus algorithm. We have a quorum of server. We primarily want to have an odd number of servers. It can be 3, 5, and 7 so that we can have a consensus. We make sure whatever we try to commit has an approval or an acknowledgement from at least more than half of the servers. So essentially, the quorum of servers should be around 3, 5, or 7. And a Raft cluster operates with a minimum of n by 2 plus 1 votes in favor of a specific server. So it should be n by 2 plus 1 votes. So every time when some commit has to happen, it needs to receive a vote from n by 2 plus 1 server. If the number of servers are 3, then we need to have at least 2 votes. If the number of servers are 5, then we need to have at least 3 votes. If the number of servers are 7, then we need to have the votes of maybe more than 4 servers. So this is how we make sure there is a consensus from the number of servers. There are typically 3 states of a server. So let me write down. The first is leader. Leader is the one who commands the other servers to append the data or commit the data. Second is follower. Follower are the ones who follow the leader. Whatever leader says, they have to do it no matter what. Third is candidate. The candidate servers are the ones who are eligible to become a leader. They initiate a process to be elected as leader. So let me just draw it for you. We have a leader, then a server known as follower, and another as. Now the Raft divides its operation into variable time lengths defined as terms. The term is increasingly monotonic. Each term indicates a start of a new election in which one or more candidates run for the leadership role. If a candidate succeeds, it becomes a leader of a new term. Sometimes the election results in a split vote scenario, resulting in no leader of that specific term. To make sure that there is no draw in terms of election, the terms have randomized timestamp. The timeout for each of the term will be randomized. They can start at any time. There is no fixed time. That is the beauty of the Raft, that an election can happen at a random time. Each candidate can start an election after a randomized time that is fixed for it, and then a new voting starts. And when the new voting starts, a new leader gets elected, then the followers get changed and they start following the new leader. After a few time or a few random time, another leader or another candidate starts the election process, and then we have the same scenario of election, then a new leader changes. Then we primarily use RPC call, that is remote procedural calls. Let me write it down for you. These are the typical communication mechanism for Raft. There are 3 types. The 2 basic types are request, vote, call. Then second is append. In the request vote RPCs, these are the type of communication which the candidate initiate during an election process to request vote from other servers. Then the append RPCs, this is what the leader initiates. These RPCs are primarily used for writing new log entries to the followers and use them as a form of a heartbeat. Let's discuss about some of the high level workflow. I will tell you the basic scenario now. Consider there are 5 servers, S1, S2, S3, S4 and S5. We need to take the odd numbers because that is a recommendation from the paper. Client sends a request to server 1, which is the leader here in this case. Then the leader sends the append entry request to all the servers. So we have append here, similarly to S3, S4 and S5. Once we send the append request to all the servers, there will be acknowledgement from all the servers. In this case, it's not necessary that we might get a acknowledgement from all the server, but we can get acknowledgement from the max number of server. In this case, since there are 5 server, even if we have an acknowledgement for at least 3 server, it is good enough. After getting an acknowledgement, S1 commits the data to itself. So it commits after getting the max number of acknowledgement. It sends the commit request to all the server which are attached to it. So it will send commit command to all of them. Once it has committed, it sends the reply back to the client. That is okay. If you see in this case, it shows that the commit has happened to the max number of servers, that is n by 2 plus 1 number of server. In this case, if the commit has happened for at least 3 servers, then it will send the OK response to the client. Internally, the structure looks like here. So this is server 1. Let me just draw how the structure looks like. So this is a key value storage. We have some key values. Then we have logs, which are append only. Similarly, we have S2. Then we have S3. The structure is similar in all of them. We have a key value pair here. Then we have key value pair in S3. Similarly, logs are there. So the request comes here. It appends the log first instead of writing to the key value pair. Once it appends the log, it also sends a request to all the servers. And after getting an acknowledgement from all the servers, then it will commit the value to its key value pair. And once it receives the maximum number of acknowledgement, that is n by 2 plus 1 number of acknowledgement, it will respond to the client. This is how a usual Raft works. Now, another scenario comes, what if the leader fails? So let me take this. S1, S2, S3, yes, and S5. It sends an append entry to all the server, and for some of the other reason, S1 fails. In this scenario, what happens is the re-election will start after the timeout. Previously, we discussed every server has their random timeout. Whichever is the nearest timeout, whenever that is reached, the election will happen. In this case, if leader fails, we will have re-election on the nearest timeout. There can be another scenario. What if a candidate fails? We have S1, S2, and S3. I've reduced the number of servers in this case because if I keep on working on 5 number of server, it will take too much time to explain you all the scenarios. So I'm reducing it for 3 for now. For example, this is the older leader, that is leader 1. Now the timeout has happened. S2 is the candidate server. It sends a request vote. After that, S3 sends acknowledgement and S1 sends acknowledgement. and then S2 suddenly fails. So what will happen is that all the servers will keep on waiting, and after a predefined time they will time out. Once a timeout has happened, and then there will be re-election. So as a gist, a candidate starts a request for voting, and after receiving the acknowledgement it suddenly fails. All the servers will keep on waiting, and once the wait time is over, they have a predefined wait time, they will time out, and then a re-election will happen at the specified timeout defined for all the servers. You remember, like, every server has a time in which they will start the re-election, so it will wait for the next election to happen and start the election again. This is how the candidate failure is solved. Another scenario can be that the follower fails. In that case, the leader will keep on sending the request to the follower. So leader will send, and it will keep on sending till the time it receives an acknowledgement from the follower. So it will wait for the follower to come up and write all the requests and send back the acknowledgement to the leader. This one is a pretty straightforward scenario where it just waits till the time the follower comes up and makes sure that the follower has all the updated values. Let's discuss how a leader election happens in a Raft algorithm. This Raft algorithm is designed for managing replicated logs in a distributed systems. The leader election is a crucial part where nodes elect a single leader to coordinate the operation. This process ensures fault tolerance and consistency. Below, I'll explain the key steps for the leader election process, focusing on how a candidate wins the election. Initially, all the nodes are followers. In Raft, all nodes starts as follower, listening for heartbeat from a leader. If current leader fails or a follower's election timeout elapses, typically it's around 150 to 300 milliseconds to avoid the split votes, the process begins. This timeout triggers a follower to transition to a candidate state. After the timeout, the follower increments its current term. It's a monotonically increasing number. For example, if it was 2, it will increase it to 3 and then votes for itself and becomes a candidate. It resets its election timer, then it prepares to solicit votes from other nodes. This prevents multiple simultaneous elections in most of the cases. The candidate then broadcasts request-vote RPCs to all other nodes in the cluster. Each request vote includes the candidate's term, its node ID, and detail about its log. The details include the last log index and the term to prove it's up to date. Peers will only grant a vote if the candidate's term is higher than theirs and they haven't yet voted in this term, and the candidate's log is at least as up to date as theirs. Then only they will vote for that request. In the next step, the receiving nodes check the request vote criteria. If valid, as we discussed previously, they grant the vote by responding with a vote granted message and reset their election timers. They update their voted for variable to the candidate's ID for this term. Votes are only granted once per team. If a node receives a request vote with a lower term, it automatically rejects it. This step can lead to split votes if multiple candidates emerge, but the higher terms resolve conflicts. In the final step, the candidate tallies the votes. If it receives votes from the majority of the nodes, that is at least 3 out of 5 or 5 out of 7, it wins the election and then transitions to the leader state. It immediately sends AppendEntries RPCs to all the nodes to establish authorities, prevent new election, and start the replicating logs. If no majority is reached before the timeout, the election fails, terms increment, and new election begins. This selection when ensures only one leader per term, and a leader will eventually be elected if there is a majority of live nodes. This process is designed to be safe where no two leaders can be there in the same term and live together. We discussed about the cases where the candidate might lose and they might be rejected. These are the conditions. The candidate is only voted yes if it has higher term in the last entry, or it has a same last term greater than equal to the longest length till the time they have seen. So this is the scenario in which the candidate will lose the elections. Let's discuss how the log replication happens. Assuming we have three servers, S1, S2 and S3, and S3 is the leaders. The entries in the servers are 3, 3, 5, 6, which are on indexes 10, 11, 12, 13 and 14. The leader has few constants that are stored in the server. One is the next index. The next index is the latest index that the leader is on. It also stores the next index values for the follower server. In this case, S2 is on 12 and S1 is on 11. Apart from that, it also stores the previous log index for the current server and the previous log term, that is 5 in this case. So let's see how the replication happens. First, it will check on the 13th index. Its value is 6. What is the value on S2 and S1? It is null. So essentially, the next index will move backward. It will now go here and we can remove this value. It will check the value in S2 and S1 again. Here we see it has 4, which is not equivalent to the current value of 5, and S1 is null. It will go one step back once more. So it will go here and we'll cross this. Now you see that the value in S2 is same with S3. So it will copy all the values after these to the S2 server. Here it will change this value to 5 and append 6 over here. After that, it will change the next index for S2 to 13. This is now backed up properly. We'll go to S1 now. In S1 again the value is null, so it will go one step back once more. Let's close here. Here the value of S3 and S1 are same. So it realizes up to this point the value is same. It will copy all the values from this current index. So it will copy 3, 5 and 6. It will update the next index for S1 to 13. And from here on, all the servers are synchronized. And it will go back pointing towards the next index, that is 14, and from here on the logs will be replicated asynchronously in the proper format. This is how the replication works. Raft also accomplishes log compaction. This is required because we want to make sure we are not appending and making the log files so large that it becomes so difficult to search. These log searches are typically disk searches, because in the files we write to the disk and it might take a lot of time when the disk search happen. To safeguard the time and avoid search time, we make a snapshot of the logs. In this scenario, let's take the example of a typical log entry. So we have log indexes labeled as 1, 2, 3, 4, 5 and 6. In the log entries, we have the terms labeled as 1, 1, 2, 3, 3 and 5, and the value to be appended. First the value of x is equal to 2, then x is turned into 5, then x is turned into x is equal to 5, and then y is added as 5. So these are the values appended in the key value pairs. If you see the snapshot how we store it, now we create a snapshot at index 5. In index 5 we mark what the term was, that is the term was 3, and the state machine value, that is x value is 5 and y's value is equal to 5. This is how we store the snapshot value, and after that we append the rest of the values after that. So the sixth index value is set to x is equal to 5. This is how we keep on taking the snapshot and discarding the other log values. This way we can save a lot of spaces and make sure we have the latest data. It is also easy to get a backup. Whenever a server crashes, we can just read the snapshot and start from there instead of recomputing from the start of the append or the log file. Now, some of the scenarios where you should not be using Raft. If it's a single server application, there's no need to use Raft if we need maximum write throughput. Instead, we can use eventual consistency. In this case, we are okay with using eventual consistency. Then the data doesn't need to be strongly consistent. In that case, we should not use Raft. Then we cannot tolerate any latency increase. In that case, we should not use Raft. Some of the places where we should use Raft is where we need strong consistency. We must survive server failures, then coordinating the distributed states, where we want to do configuration management, where leader election is needed, or we can tolerate slight latency increase. This is where we should use the Raft. That's about Raft algorithms. If you made it this far, you know more about data architectures than most of the senior engineers. Hit that like button if this helped you understand this algorithm. Subscribe for more system design content and drop me a comment if you have used Raft or any other consensus algorithm. Thank you and see you in the next iteration.